Hi, everybody. I hope you're having a wonderful I/O. I know I'm having a great one so far, and it's been a fun time. Lots of great announcements and lots of good stuff going on in the community. If you got a chance to check out the adventure, I'm hanging out there most of the time, so please feel free to join in, ask any questions that you have there. We're going to be today going through this workshop around anomaly detection using machine learning and using TensorFlow. And we do have a question and answer window on the side, so feel free to use that to ask any questions. I'm going to be going through some slides at the beginning to talk about how anomaly detection works. And then we're going to be doing like a hands-on workshop, going through some code, going through a collab. And then at the end of that, hopefully we got a little bit of time for some Q&A. But if we do run out of time, then we'll be over in the I/O Adventure to be able to answer your questions. So first of all, I want to talk a little bit about how anomaly detection will work from a machine learning perspective. But in order to be able to do that, let's understand really what machine learning is all about. Now, you might be familiar with the term machine learning for doing things like classification or for doing regression to be able to predict values, or even some novel uses of machine learning in creating stuff. So things like generative adversarial networks or variational autoencoders that can actually be used to create new material. What we're going to be looking at today is a really novel and really fun example of using machine learning and actually using errors in machine learning to understand if a piece of data is correct as expected or if it's anomalous. But in order for us to be able to do that, let's understand a little bit about what machine learning really is. So I always like to use a chart like this one to describe programming. And traditional programming is where we have a problem that we want to solve. Maybe that problem is to calculate some data about the value of a business, or maybe it's to detect an activity if we're building a fitness app. And generally, there's all of these kind of problems that we have to solve. And what we use is rules in a programming language that we create. Those rules will act on data, and then they will give us back some answers. So, for example, a common thing in stock and in understanding finances, there's a thing called the price over earnings ratio, or a PE ratio. And that's pretty simple, where you have a piece of data, which is the current price of the stock. You have another piece of data, which is the earnings of the stock. And then you can calculate P over E by writing code. Maybe it's Java or C Sharp or whatever. And you're then creating those rules in that code that acts on that data to give you an answer. And it's a very simple, very trivial example, but that's generally how programming in the traditional sense works. So when we want to talk about machine learning, I like to flip it around to look at it this way. And with machine learning, it's almost the same thing. But instead of us trying to create the rules ourselves in a programming language, we instead have a bunch of answers and we have a bunch of data. And we'll have a machine figure out how to map those answers to that data. And when it does that, it will actually figure out the rules for us. So for example, for a simple example I spoke about earlier on, like a price over earnings ratio, we don't really need to do that. It's very simple for us to write the rules. But think about something that's more complex. And in this case, maybe activity detection that I spoke about earlier on. You're building a fitness app and you want to know if the user is running or if the user is walking or biking or some other activity. The rules that you'd have to write for that are very difficult. You know, you may have access to data from the accelerometer on their device and you say, well, at a certain speed, they might be walking or biking or running, but different people walk at different speeds, different people bike at different speeds. You might run fast downhill and slow uphill and things like that. So the amount of rules that you have to write to be able to do that is very difficult. So the idea behind machine learning is if I've got all of this data and I've labeled that data, this is what walking, this is what biking, this is what running looks like, then I can have a machine look at the patterns between the walking and the data for walking and the fact that I said that this is walking, the data for running and the fact that I said those type of things, figure out what those patterns are, and then establish a set of rules from that. And that's where machine learning is traditionally very useful. You want to build a classifier to understand the contents of an image. You'll train that classifier on lots of images to say, this is what a dog looks like or a cat looks like. You want to do activity detection. You train it on lots of examples and that kind of thing. But for anomaly detection, we're going to use this, but in a kind of a novel and interesting way. So let me first, for example, take a look at these values here. Now, so these values are from the common data set called MNIST, and it's a data set of 70,000 handwritten digits where the value is like between 0 and 9. And it's commonly used to build an image classifier so that if you then create a handwritten digits, the image classifier will be able to tell and read your handwriting if it's a digit from 0 through 9. But what we're going to do here is we're actually going to compress the data in these images into 32 bytes. So each of these images actually has 784 bytes to begin with. It's a 28 by 28 image with up to 255 values. So it's a single byte image. And each one has, so as a result, each image has 784 bytes being able to use to store it. So if we were to write an algorithm to compress these, we could do that with something like a zip or a JPEG or run length encoding or something along those lines. But another way that we could do that, given that we have the data, is that we could write a machine learning algorithm where the algorithm would learn a compression of that data that could then be reconstructed. And in this case, this is what has happened here, where I have these digits, 5, 3, 8, etc. And using a machine learning algorithm, I've trained a model to be able to compress it in a certain way so that when you decompress it, the error is relatively low. And as a result, the decompressed version that you see at the bottom here looks kind of sort of like the original image. It gets off a little bit, particularly with the 8s. As you can see, those 8s don't look too good. And maybe that second one, the 3, doesn't look great. But things like the 1s and the 9s and the 5s and the 7s, they're all looking pretty good. Now, remember, we haven't written an algorithm here to do the compression and decompression. We're not doing traditional programming where we'd figure out a compression algorithm. We've trained a model to come up with a representation of those 784 bytes into 32 bytes that when it reconstructs from those 32 bytes, it'll reconstruct that with a relatively low loss. And that's the very important thing that we have to remember when we want to do, when looking to spot anomalies in data, that we'll have something where we have relatively low loss for the data that we're training the model with. So now if I were to bring in another piece of handwriting that might be the letter W, when it would try to reconstruct that, it would do a really bad job of that because it was never trained on a W. It was only trained on 0 through 9. So then we could say from the reconstruction, the loss of the reconstruction is very high. Therefore, this value is anomalous. So that's the general idea that we're going to be looking at here, creating something called an autoencoder, where we're going to encode data. We're going to then reconstruct that data, and we're going to learn a model that will reconstruct data from the original data with a low level of loss and therefore a high level of accuracy. So what does this look like? So the idea behind an autoencoder is pretty simple. It's effectively two neural networks where you have an encoder and you have a decoder. The idea of the encoder is that we take data with a high level of dimensionality. I've just represented that with 5 blue blobs here. And what it will do is we'll learn a way for it to represent the data in a much lower dimension. In this case, with the bottleneck here in the center with the 2 gray blobs. And then the network will learn how to reconstruct the data from what's in the bottleneck to the 5 blobs on the right-hand side, which is the same dimensionality as the original data, hopefully losing as little information as possible, having as low a loss as possible, so that our reconstruction will look a lot like our original image. Now, remember, we could have written an algorithm for this ourselves, like a JPEG or zip or run length encoding or something like that, but that's not the point here. The point here is for us to build a machine learning model that learns the representation for the input data. And we can then utilize that model on future data that does not look like the input data, so that we would use that to be able to recognize anomalous data, i.e. data that looks different from our input data. And that's the one thing to remember. It's like we are kind of using autoencoders in that kind of a novel way, that we deliberately want to build one that doesn't work in some scenarios. And when it doesn't work in those scenarios, that's when it's spotting anomalous data. So an autoencoder looks like that. And the code for an autoencoder for the digits that we're just looking at would look a little bit like this. It's pretty simple. This is pretty low dimensional data. Like I mentioned, it was just 28 by 28. So it's 784 bytes of data. But we'll see when we look at it that our code has both an encoder and a decoder. So our encoder, in this case, we're just using a simple DNN, a dense neural network, where it's taken 784 bytes in, and then it's using a dense to reduce that to 128, another one to reduce that to 64, and then another one to reduce that to 32. So earlier when I showed the diagram of the 5 blue blobs becoming two gray blobs, effectively what we're doing here is we've got 784 input values that we're going to reduce to 32 input values. Remember, we're not doing any coding here. This is all going to be the neural network learning what the values of those 32 bytes should be to represent the original 784 so that we can, when we decode them, we'll end up getting something that has low loss and therefore looks like the original. And similarly, the decoder, well, we can see here, these are the 3 layers, again, 784 to 128 to 64 to 32. And then similarly, the decoder is going to go in the opposite direction. So it's going to take 32 bytes or 32 values, it's going to inflate those to 64 to 128 and to 784. So here I've created a class in Python, and this class in Python has an encoder method and a decoder method. The job of the encoder is to take the values, like I said, from that high dimensionality down to the lower one. The job of the decoder is to take them from the low dimensionality back up to the higher one. And because this is just a neural network defined using TensorFlow and a Keras Sequential, when I train this model, that's what it's going to do. It's going to take the input digits. It's going to figure out what are the correct weights and biases for these dense networks to end up getting that encoded value, that latent value, to learn what are the weights and biases of the decoder network to be able to turn that into something that looks like the original and will define it looking like the original as having a low loss. Okay, and again, you can see here, this is where the decoder is inflating it back to the 784. That's the number that you want to realize that the input values were 784 because that's the size of the image in MNIST. Okay, so now when I call this class and I'm passing data to it, it's going to create an encoded by taking the input, which in this case is just called X, passing that to the encoder, and then it's going to get that encoded value, pass it to the decoder to get back the decoded value. So when we call this after it has learned and it has been trained, we're going to give it an input image. It's going to give us back its decoded version of that input image, and we can compare these with each other to see just how good this model was at learning that representation. So like I said, if I passed it a handwritten W or something that doesn't look like a handwritten digit, what it would return to me would look really bad. And that's what we want. Okay, so going back, here's a few other digits where this network has been used, where it learned the representation from the 784 bytes on the top, turned that into a 32-byte representation, and then decoded it back out as 784 bytes at the bottom. And here's some examples where it did really well. And as you can see, generally, this model, when the image was a little bit more bold, it kind of did better. And when it was a little bit skinnier, like the 6, that's second from the right, it didn't reconstruct that very well. But again, it looks like a 6, and we're getting relatively low loss when we're doing this. And realizing, again, that the important thing here is that we want to learn that representation in the middle, and that's what the encoder part of the neural network was doing. So it was taking the 784 input and giving us those 32, and that 32, which was the third of the layers in the encoder that we looked at, that's what we're seeing here. And I was just plotting those out in this one so we could see what they look like. Okay, so going back to this diagram, that's the whole idea behind an autoencoder. Now, you may have heard of something called a variational autoencoder. We're not going to use that, and I'll explain why in a moment. But the goal here is that the autoencoder takes high dimensionality input, learns a relatively low dimensionality bottleneck or latent representation of that, and it gives us a high dimensionality output, which was the same dimensionality as the original input. Now, I've been drawing it as a dense network, but of course it doesn't have to be dense. And if you're using images like we were using with the handwritten digits or other things, those layers in the encoder, those hidden layers, they could be anything. You can use convolutional neural networks, for example, for that in order to learn a better latent representation. And the decoder, if we could use them to give us a better output, we can do that also. So it doesn't have to be dense. In this example, I was just using dense to make it a little bit simpler. Now, a variational autoencoder, the goal of that is that the latent representation, when you decode it, you're actually adding random values to it. So it can learn an effective decoding for variables and for values that it hasn't previously seen. So this is really useful if we want to have a very powerful encoder-decoder architecture that is able to reconstruct data based on things that it hasn't previously learned. But that's not what we want to do when we want to do anomaly detection. We don't want to use the variational autoencoder. We want to make sure that the decoding part of this will only work really well for the type of data that it was trained on. So if we're giving it anomalous data, it's going to fail, and that's what we want. So a lot of times the question, like when we're looking at something like this, is like variational autoencoders are better than autoencoders. Why not use a VAE instead of an autoencoder? Well, that's really why. In some ways, we actually want it to fail, and the variational part of a variational autoencoder would hide that for us. So realizing if you're going to do anomaly detection, and one thing just is to manage expectations, this is a very basic example that we're going to be showing today that we're going to be working through, but hopefully it's going to show you the concepts that you'll need to know to make this to be able to work effectively. Okay, so if I move to the next slide, remembering the latent representation is what this is all about. The encoder is going to learn that, the decoder is going to learn from that. So here's an example using a similar data set to MNIST. It's called Fashion MNIST. And in the collab that you'll be using a little bit later on, you actually have the code to do this. And in this case, at the top of the diagram, I use the DNN to be able to learn a representation of the data and decode it. And in the bottom of the diagram, I use the CNN. So for example, if we just focus on the top of it for the moment, and we take a look at some of the images in the top, the bottom here is where I use the CNN. If we just look at the top again and some of the images at the top, take a look at these three shoes, for example. Now, these three shoes were encoded into the representation you see in the middle, and then they were decoded afterwards. And if you take a look, particularly at the high heel shoe on the right, the decoding of that was pretty blurry. And again, this was using a DNN. When I use the CNN instead, you can see now the decoding from the CNN, and admittedly, the CNN was using more data to represent it as well. But the idea with a convolutional neural network, remember, is that a convolutional neural network can learn features in an image. And then when you have those features represented in your latent representation, then those features could be re-inflated from that by the decoder. And as a result, we're getting a sharper image here. And again, looking at that high heel shoe on the right, when I did it using a DNN, it was pretty blurry. But when I did it using the CNN, it's a much, much sharper image. So often, if you want to do a really good encoder-decoder architecture, look beyond DNNs, consider other layer types that are appropriate for your data. And for example, for images like this, of course, that would be CNNs, convolutional neural networks. And again, similarly, if we look over on the right here at this jacket looks like one of those puffy jackets that has those horizontal lines in it. When we did the latent representation of it and then reinflated that latent representation, we got a blurry jacket. But when we did it using the convolutional neural network, as you can see here, we began to see a little bit of that detail. Again, not all of that detail is there. It does look a little bit better. We're seeing some of those horizontal lines, but we're not seeing all of them. So we're getting a better reconstruction, i.e. the loss is lower. But again, it's not a perfect reconstruction. Okay, so how do we use this for anomaly detection? And so the idea with anomaly detection is that we have an ECG, and we're going to give an input of an ECG. We're going to learn a latent representation of that ECG, and then we're going to reconstruct the ECG from the latent representation and measure the error. So if we look at the ECGs at the top here, you can see the original ECG on the left, and then on the right, we have the reconstructed one. And those red shaded areas are where the reconstructed one differed from the original. At the bottom, we have an anomalous ECG. And on the right of that, we see the original anomalous ECG, the reconstructed one. And again, those shaded errors are the difference between the two of them. To the human eye, it may not look like there's much difference in these errors. So sometimes something like this is hard for us to determine with the human eye if this is anomalous or not. But when we use a machine learning model and we can get a little bit deeper into the statistics behind it, we may be able to detect if there's anomalies here. So let's take a look at how we're going to do this. So first of all, here's a normal ECG that I've shown, similar to one that I showed earlier on. And we want to understand the data of a normal ECG. It's a time series value. The one that we're getting from the data set that we're going to be using today has 140 points in it. So it's a time series value of 140 points. Those points are within 1 and a certain number. but we're going to normalize that to be between 0 and 1. So the first thing that we want to do to make sure all of our data is consistent, make sure the dimensionality is right, we want them all to be 140 data points. We want them all to be normalized. And now we're just taking a set of 140 values between 0 and 1, and we're going to train a neural network off of that. Now, earlier when we were looking at using the MNIST digits, we had 784 data points that were between 0 and 255. So this one's even simpler. We've only got 140 that are normalized between 0 and 1. So then we'll define a neural network, and this one will look very similar to what we showed earlier on for the MNIST detector. But because I mentioned the data is simpler, then the values within the neural network and how I'm defining my architecture is also going to be simpler. So recall that I have 140 input points. So those 140 input points, I'm going to pass through some dense layers that reduce the dimensionality to 32, then to 16, and then to 8. So my 140 input points for an ECG, I'm going to reduce that down to 8 points. I'm effectively compressing the data. And again, going back to right to the beginning, we could write an algorithm to compress the data very effectively, like a zip algorithm or a run length encoding or something like that. But that defeats the point. The idea here is that we want something that compresses the data effectively for one set of data, which is the real data, but then doesn't compress it effectively or doesn't reconstruct it from a compression effectively for a different set of data. And that's how we're going to spot anomalies. So remembering now our encoder is going to learn how to represent those 140 data points as 8 data points. And then it's going to learn there's our 8 data points in our latent space, which is the latent representation that we saw in the middle here. In this case, it's only going to be 8. It was 32 for the handwritten digits. And then our decoder is going to reinflate the data. So it's going to take the data that we have, those 8 data points, reinflate to 16, to 32, and then up to 140, remembering that our ECG had 140 data points in it. So again, this is a neural network. It's randomly initialized weights. We're going to send it a bunch of data. The data that we're going to train it on is all ECGs that are good, no ECGs that are anomalous. And as a result, it will learn how to encode and compress a good ECG into 8 bytes and then recompress that into something that has relatively low loss. So therefore, if we pass it a bad ECG, by definition, the compression will be poor. The reinflation of it will be poor. It will have high loss. And based on that loss, we'll be able to determine if our ECG has anomalies or not. Okay, so if I then, sorry, just having a little trouble with the slides. Okay, here we go. So remembering it was those 140 data points in a normal ECG. So now let's take a look at, here's a normal ECG on the left, those 140 data points between 0 and 1. That got compressed into 8 bytes. Those 8 bytes were then reinflated into another 140 bytes, and you can see them on the right. So this was how we got a normal ECG and compressed it and reinflated it. And we can see that other than, the strange few peaks on the left of the reconstructed image and the missing dip on the right, as well as the slightly smoother curve, it has the same general shape as the original ECG. And as a result, it's going to be relatively low loss when we measure the loss on this, and we know that it's not an anomalous ECG and it's a good ECG. And if, for example, we do that here, so I've plotted one against the other. The blue was the original input image, red was the reconstructed image, and then this coral shade in between the two is our error, and we can measure that error. And similarly, if I take a ECG that is anomalous, so on the left is a bad ECG, on the right is the reconstruction of that ECG. And you'll notice that when it reconstructs an ECG, because it learned how to represent an ECG using many good ECGs, that the latent representation of that, those 8 bytes, will get reinflated in many ways to look like a good ECG. And as a result, the difference between these two images is much greater. And that difference tells us that we had an anomalous ECG to begin with. So if I reconstruct it here with blue being the original, red being the reconstruction, and then this coral shade is the error, again, to the human eye, it may not look like there are a lot of errors here, And it may look as just as erroneous as the original one. But when we start measuring this using Python and using TensorFlow, we'll see there's a huge difference in the error between this one and the previous one. And then that becomes our signal to determine that this was an anomalous ECG. Okay, so let's take a look at the code for this. So now it's a case of I've created the autoencoder that I created earlier on. And whoops, sorry, let me go back. So I created an autoencoder earlier and I trained that autoencoder. And on the first line of the code here, I'm passing a set of normal training data to that. What that's going to do is it's going to encode it, it's going to decode it, and then it's going to return us the reconstructions. So I have my set of normal training data, and then I have the reconstructions of that training data. So then in tf.keras.losses, I can use the mean average error to count the average error between these reconstructions and the normal training data, and then I can plot that out. So when I plot that over my normal training data, I'm going to see my training loss looks a little bit like this. So the vast majority of the training has a loss of about 0.03 or less. Some of the data in the training set has a little bit more than 0.03, but just eyeballing it here that I can see from my training data, which remember is just good ECGs. There's no bad ECGs mixed in. So my training data with just good ECGs has a loss of like about 0.03 or less. And then if I take a look, for example, at the mean of them and just increase, like take a look at one standard deviation above that to get my threshold, that gives me a threshold of 0.035. So again, going back to the previous slide, if you look at where 0.035 would be, you can see the vast majority of the data is to the left of 0.035, meaning its loss is less than 0.035. And as a result, we could say, well, if we pass a piece of data, we get the reconstruction of that data, we measure the loss on that. If it's greater than 0.035, then there's a good chance that that's anomalous. But let's confirm that. So if I then look at my anomalous test data, so I now have, I'm using the same algorithm, but I have a set of anomalous test data, which are ECGs that were bad and or anomalies and not the same as the ones that I trained with. I can pass that data to my autoencoder to get a set of reconstructions. I can count and I can measure the mean average error between the reconstructions and the anomalous data, test the data, and then I can plot that out. And when I plot that out, I'm going to get something that looks like this. And now we can see here that the vast majority of the highest peak here is at about 0.05. But if we remember the point that I measured earlier on of 0.034, that's right about here. So now I have a very, very clear signal that if I pass my data to this encoder, I get a reconstruction from it. I then take a look at the loss. All I have to do is take a look at the loss value. If it's less than 0.034 or 0.035, if I round up, then the likelihood is that my data is good, that this is a real ECG. There's no anomalies here. If it's greater than 0.034, the likelihood is that it's bad and there are anomalies here. So as a result, just using an autoencoder to be able to encode to learn a representation to encode my data gives me the ability to have this algorithm to spot anomalies. And again, this is a very simple one that we're doing here. It was just 140 bytes of data. If you're doing this for anomaly detection in the real world, you're going to be using something a little bit more complicated, but hopefully this is a good introduction to it. So we're going to switch now to a Colab. And in this Colab, I'm going to step through the code that I showed here. This QR code has the URL. It's the same URL that you can see here if you want to follow along, so you can try it out for yourself. I will note that the code lab that we're going to be looking at does a number of different things with autoencoders, but we're just going to be doing the part of the autoencoder that's used for anomaly detection. So take a quick look at that. Go visit that URL and let's go and we can switch to the demo now so that we can see it in action. Okay, so that code lab that we just mentioned I'm sharing it now in Google Colab. So I mentioned earlier on that there are three things that it's going to be doing. The first one is the fashion MNIST. The second one is going to be denoising fashion MNIST. And the third one is anomaly detection. So we're going to switch to the third one. But first, before we do that, we need to import TensorFlow and other libraries. So I'm just going to run this cell. And what this is doing is just importing everything that you need for TensorFlow and NumPy and Pandas and all that kind of stuff. Okay, so the second thing that says load the data set is for fashion MNIST. I'm going to skip beyond that and scroll all the way down to the third example in this code lab. And that's down here for anomaly detection. So again, this is it has, as we can see, it has 5,000 ECGs. Each of these ECGs is 140 data points. The data set has them labeled to be either 0, which is an abnormal rhythm, or 1, which is a normal rhythm. Now, if we were training a classifier, we would want to be able to train a classifier to tell the difference between an abnormal and a normal rhythm. And we would use both of these. But in this case, we want to do anomaly detection. So we're actually going to filter out the data set to just the ones with the normal rhythms. So keep an eye out for that. The first thing I'm going to do is just download the data set and run it. And we see we can just use pandas. It's a CSV. So we're downloading the ECGs as a CSV. And when we use pandas, we can take a look at the data. If I scroll all the way to the right, we'll see that there were 140 data points in the data. And then the final column is the label. And again, it mentioned that it's 0 for an abnormal rhythm or 1 for a normal rhythm. So what we're going to do is we're going to filter out all of the normal rhythms. The first thing we want to do is get our labels. So the labels is the rightmost column. So this piece of code is just going to get the raw data, get the rightmost column, turn that into our labels. And then the rest of it, of course, are the 140 data points for the ECGs. So then we want to normalize the data, and we're just going to normalize the data by getting the min, getting the max, and then dividing the data minus the min by the max minus the min, just to get a basic normalization of the data. So we have our training data, we have our test data, and from that, and we're going to cast that data then into float 32s. So these float 32s will be used to train the network. Now, the important thing here is that we're training an autoencoder to learn a latent representation of normal rhythms. So we only want the ones in the data set that are ones. So here we're going to separate the normal rhythms from the abnormal rhythms. And this piece of code will do that for us so that we split one from the other. And we end up, by the time we're done with this, is that we have a set of normal training data and we have a set of anomalous training data. And then we also have a separated set of normal test data that we can use to test it, and anomalous test data that we can use to test the anomalous data set with data that it wasn't trained on. So if we plot a normal ECG, this was just how I was plotting it, and use the same plot that we saw on the slides. Here's a normal ECG. We have 140 data points. It has been normalized, so it's between 0 and usually it should be between 0 and 1, but it looks like most of them are generally between 0 and about 0.6. And then if we plot an anomalous ECG, now remember the anomalous training data were the ones that we split out. I'm just taking the first item in that one. An anomalous ECG looks like this. We can see it looks very different from the shape of a normal ECG. So by the human eyeball, we could say this looks anomalous, but I don't know what a good ECG is supposed to look like. This might be a good ECG, but when we use the encoder to be able to learn the representation and then decode it, hopefully this is the kind of thing that we'll be able to use to have a machine spot the anomalous ECG for us. So now here's where we build the model. So again, it's the encoder is going to be taking the 140 values. It's going to be then giving us a dense representation of 8 values, and that will be that latent representation of the ECGs that are normal ECGs. And then the decoder, as we saw on the slides, is just going to reinflate that back up to 140. So let me run this, and then we're just defining our anomaly detector. You see it's a very, very simple dense. If your data is more complex, if your data is higher dimensionality, you're going to be using a more complex algorithm here. You're going to be using a more complex architecture. But this one's very simple, just to keep it quick. We then, in Keras and TensorFlow, once we've defined our neural network, we compile it. When we compile it, we specify the optimizer and the loss function. I'm just using a simple atom optimizer, and MAE stands for mean average error as my loss function. So I'm just going to compile it with that. I'm going to train it. So it's going to try to fit the normal training data to the normal training data. It's going to just train for 20 epochs. And then we're going to just test validation on the test data and, do things like shuffle the data as we're doing it. And we can see it's running pretty quickly, and I'm only running for 20 epochs. Keep an eye on the loss. Our loss starts at about 0.05. After 20 epochs, it's down to about 0.02. We could probably train it a little bit longer if we wanted, but I'm just going to train this simple one for now. As we saw, it just took a few seconds for us to train it. Again, we're just doing a very simple example here. You might want to use a more sophisticated architecture, train for longer, experiment with different loss functions and optimizers and all that kind of things to get your loss as little as possible. But when we plot it, and we can see that our training data in the blue, our loss ended up getting really low, about 0.02. And if you remember from the histogram I was showing earlier on, that was the expectation. And our validation data, which is anomalous, the loss is much higher. And this is what we'd expect. Now, if you were building a classifier at this point, you might be worried about overfitting. But in this case, this is what we actually expect to happen. We want data that's anomalous to have a higher loss. That's if there's any golden rule of using an autoencoder for anomalous detection, that's the signal that we want to have. So now if I go and I take a look at my encoded images, and so I take a piece of normal test data and I, plot this out, we can see what we were looking at earlier on, and we can see the difference between the two of them being the shaded area. That's our loss. And then if I do a similar plot for a anomalous example, we have the same thing. And the thing that always confused me as a human when I'm looking at this is that the amount of coral colored space between this one and this one, I can't see a huge difference between them. And I think this is really important because if we were trying to eyeball things like this for anomaly detection, and particularly if the data was much more sophisticated, we may not be able to see it. But when we have the machine looking at it, then we're going to run the same code that we saw in the slides. And here is a case of now it's calculating the loss on all of the training data, and it's plotting out that loss as a histogram. So as we can see, the vast majority of the training data was to the left of about 0.03 something. Some of the training data had a higher loss. There's even some over here that has a massive loss. So we know that this isn't completely foolproof. But when we look, the odds are that a significant amount of our data, 99% plus, is below a certain value. Then we can start building an anomaly detector with some level of certainty. And so if I just then take the training loss data, the mean of that, the standard deviations, calculate the thresholds. In this case, it's a little bit different from the one I had in the slides, but it's in the same kind of ballpark. It's about 0.030. So this was just one strategy that we did where we say one standard deviation above the mean. You don't have to use that strategy, of course. There could be a number of different ways that you could calculate this, and you could try to figure this out. It's up to you. It's up to your data, and it's up to really the needs of your system. But this is just a very simple way of doing it by calculating the average, getting one standard deviation and going one standard deviation above that. So now if we do the same thing with our anomalous test data, so again, I'm just creating the reconstructions out of that. I'm calculating the mean average error between the reconstructions and the original data. And so the original data was passed into the network, got encoded, got decoded, and gave us back our reconstructions. And then we measured the loss of the reconstruction against the original. And for the anomalous data, it ended up plotting something that looked like this. And as we can see, if we remember our value here of 0.03, if we look at 0.03 on this chart, that the vast majority of the data was above that. So we realized that this is a pretty good algorithm in this case. And the algorithm was to get the training data, which is the good ECGs, calculate the loss on that, take one standard deviation above that loss, and assume everything below that value is a good ECG and everything above that value is anomalous. And this ends up being much more reliable in being able to spot anomalous data because, other than these 3 or 4 data points, everything to the right of 0.03 is anomalous. And I think that's much more reliable than just eyeballing the charts like we're doing here. And that's ultimately how this will work. So now we can, run a predict on our model and get the stats. And then if you're the statistical type of person and you want to understand things like precision and recall, we calculate the stats on this, and we see that using this algorithm that we're using right now, it's 94% accurate at being able to spot an anomaly. And the precision is about 99%, the recall is about 90%, but I just like to think in the simple terms of the overall accuracy. So as a result, we now have a model that we are able to train on these ECGs in just a few seconds that was 94% accurate. We could tweak the architecture of the neural network. We could experiment with different loss functions and optimizers. We could pick our threshold differently if we want to get even more accurate on this. But I think for just a few seconds, being able to build this one that's 94% accurate is pretty good. Now, there's a really cool, there's some next steps that you'll see at the bottom here, and there's a really cool interactive example I'm going to show in a moment. But I would, if you go through this code lab, I definitely recommend visiting all of these links and definitely reading this blog post by Francois. And if you have the book on deep learning by Ian Goodfellow and Joshua Bengio and Aaron Curville, there's again, details on how to use deep learning to be able to do anomaly detection in that chapter. But this interactive example is really cool, and I'm going to visit that next. So this interactive example was built using TensorFlow.js. And the creator of this used TensorFlow.js, trained a model to do exactly what we were just talking about, but makes it a little bit more interactive. So we can take, for example, by clicking on the left here, we can pick some of the ECGs from the data set. It has a trained model that will then use to pass that, to get the reconstruction back from that, to plot both of them and to measure the loss. So for example, if I pick this one here, I can see then that the reconstruction is pretty close to the original and the error is pretty low. But the color coding that he used in this case makes it a lot more user-friendly, so that we can see these green ones, the model prediction is quite normal. And if we see for these red ones, the model prediction isn't quite as good. In this case, he calculated the threshold to be 0.007. He may be using a different way of measuring the threshold than we did in the code lab. But the idea here is that it's exactly the same technique. So you can see just how good or how bad your ECG is. And if you want a little bit of fun, you can actually draw one. So if I kind of draw one like this, it's clearly anomalous. There's plenty of red in here. My MSE was 0.09. They had the threshold to be 0.007. And I would challenge you to see if you could draw a non-anomalous ECG with this. I don't think I've ever been able to do one. Whoops, I went way off here. And again, even higher error. So again, really fun, really great example of how you can use an autoencoder to be able to spot anomalous data. Remember, use an autoencoder for this, not a variational autoencoder. And I definitely would say to try this out for yourself, go visit these sites and have a look and have a play with them. So that's it. That's what we wanted to go through today, to talk about how to use how to use an autoencoder, not a variational autoencoder, but how to use an autoencoder in a very simple scenario. It's to be able to use this to go beyond the normal use of machine learning and to do things like anomaly detection by looking at reconstruction error. So with that, we're going to open it up to some questions and answers. I'm going to take a quick look if there are any questions out there. Okay, so there is one question from Abhijit, and how does the performance improve when we use a Bayesian autoencoder? Does it improve? It's a great question, Abhijit, and I would say the answer to that, basically, it depends. Ultimately, it depends on your data, and I see Yash has tried it out to say he doesn't know, but say try it out to see if the performance improves. But in general, the usual thing here would be that it really depends. If your data would do better with a Bayesian algorithm on it for selection and those kind of things, then yeah, it might. But this is the kind of thing that you'd have to try for yourself. But again, it clearly depends on your data. For something simple like the ECG data that we're doing here, that would probably be overkill. Okay, were there any other questions? Let me just take a look. Fadi Badin asked if autoencoding can be used to detect anomalies in a time series. That's exactly what we just showed. And hopefully, this time series where we just took a slice of 140 items in an ECG, if you were going to do it with a more complicated time series, like maybe an unlimited one, you would probably have to window that time series into smaller slices, train it on those, and, go from there to see if you can spot anomalies in that. If it's a constantly changing time series where, at this slice, it looks like this, but at this slice, it looks very different, it's going to be harder for you to train an autoencoder in that way. In this case, it was a very controlled environment where we had those 140 data points to be able to train it on. Okay, were there any other questions? I don't believe so. Let me just check. Okay, so I think that's all that we have questions on. So in that case, I'll just say, hey, thank you so much, everybody, for tuning into this workshop. Really appreciate you being here at I/O. If you have any further questions for me or for the rest of the team, we will be over in the Google I/O Adventure. Or if you have questions about this workshop after I/O, you can still ask them on the stream. It's going to be open for a little while, and we'll be monitoring that to answer them. Or just personally feel free to reach out to me and Al Moroney on Twitter. And at that, I'll say thank you very much.